High-altitude wind power is the harnessing of the power of winds high in the sky by use of tether and cable technology. An atlas of the high-altitude wind power resource has been prepared for all points on Earth. A similar atlas of global assessment was developed at Joby Energy. The results were presented at the first annual Airborne Wind Energy Conference held at Stanford University by Airborne Wind Energy Consortium. Various mechanisms are proposed for capturing the kinetic energy of winds such as kites, kitoons, aerostats, gliders with turbines for regenerative soaring, sailplanes with turbines, or other airfoils, including multiple-point building or terrain-enabled holdings. Once the mechanical energy is derived from the wind's kinetic energy, then many options are available for using that mechanical energy: direct traction, conversion to electricity aloft or at ground station, conversion to laser or microwave for power beaming to other aircraft or ground receivers. Energy generated by a high-altitude system may be used aloft or sent to the ground surface by conducting cables, mechanical force through a tether, rotation of endless line loop, movement of changed chemicals, flow of high-pressure gases, flow of low-pressure gases, or laser or microwave power beams. There are two major scientific articles about jet stream power. Archer and Caldera calculated that, if the world's entire electrical energy demand were supplied by HAWP, the climatic impact would be negligible. Miller, Garnes, and Clyden claim that the jet streams can generate the total power of only 7.5 terawatts, and that the climatic impact will be catastrophic. High-altitude wind for power purposes. Winds at higher altitudes become steadier, more persistent, and of higher velocity, because power available in wind increases as the cube of velocity, assuming other parameters remaining the same. Doubling a wind's velocity gives 23 equals 8 times the power. Tripling the velocity gives 33 equals 27 times the available power. With steadier and more predictable winds, high-altitude wind has an advantage over wind near the ground. Being able to locate HAWP to effective altitudes and using the vertical dimension of airspace for wind farming brings further advantage using high-altitude winds for generating energy. High-altitude wind generators can be adjusted in height and position to maximize energy return, which is impractical with fixed tower-mounted wind generators. In each range of altitudes there are altitude-specific concerns being addressed by researchers and developers. As altitude increases, tethers increase in length, the temperature of the air changes, and vulnerability to atmospheric lightning changes. With increasing altitude, exposure to liabilities increase, costs increase, turbulence exposure changes. Likelihood of having the system fly in more than one directional strata of winds increases, and the cost of operation changes. HAWP systems that are flown must climb through all intermediate altitudes up to final working altitudes, being at first a low and then a high altitude device. Methods of capturing kinetic energy of high-altitude winds. Energy can be captured from the wind by kites, kitoons, tethered gliders, tethered sailplanes, aerostats, bladed turbines, airfoils, airfoil matrices, drogues, variable drogues, spiral airfoils, Darius turbines, Magnus effect VAWT blimps, multiple rotor complexes, fabric Jalbert parafoil kites, uniblade turbines, flip wings, tethers, bridles, string loops, wafting blades, undulating forms, and piezoelectric materials, and more. When a scheme's purpose is to propel ships and boats, the object's tether placed in the wind will tend to have most of the captured energy be in useful tension in the main tether. The aloft working bodies will be operated to maintain useful tension even while the ship is moving. This is the method for power kiting sports. This sector of HAWP is the most installed method. The folklore is that Benjamin Franklin used the traction method of HAWP. George Pocock was a leader in tugging vehicles by traction controls. HAWP aircraft need to be controlled. Solutions in built systems have control mechanisms variously situated. Some systems are passive, or active, or a mix. When a kite steering unit is lofted, the KSU may be robotic and self-contained. A KSU may be operated from the ground via radio control by a live human operator or by smart computer programs. Some systems have built sensors in the aircraft body that report parameters like position, relative position to other parts. Kite control units have involved more than steering. Tether reeling speeds and directions can be adjusted in response to tether tensions and needs of the system during a power generating phase or a turn non-power generating phase. Kite control parts vary widely. Methods of converting the energy. The mechanical energy of the device may be converted to heat, sound, electricity, light, tension, pushes, pulls, laser, microwave, chemical changes, or compression of gases. Traction is a big direct use of the mechanical energy as in tugging cargo ships and kiteboarders. There are several methods of getting the mechanical energy from the wind's kinetic energy. Lighter than air-moored aerostats are employed as lifters of turbines. Heavier than air-tethered airfoils are being used as lifters or turbines themselves. Combinations of LTA and HTA devices in one system are being built and flown to capture HAWP. Even a family of free-flight airborne devices are represented in the literature that capture the kinetic energy of high-altitude winds, and a contemporary patent application by Dale C. Kramer, soaring sailplane competitor, inventor, electric generator position in a HAWP system. Electricity generation is just one of the optional choices of using captured mechanical energy. However, this option dominates the focus of professionals aiming to supply large amounts of energy to commerce and utilities. A long array of secondary options include tugging water turbines, pumping of water, or compressing air or hydrogen. The position of the electric generator is a distinguishing feature among systems. Flying the generator aloft is done in a variety of ways. Keeping the generator at the mooring region is another large design option. The option in one system of a generator aloft and at the ground station has been used where a small generator operates electronic devices aloft while the ground generator is the big worker to make electricity for significant loads. Aerostat-based HAWP. One method of keeping working HAWP systems aloft is to use buoyant aerostats whether or not the electric generator is lifted or left on the ground. The aerostats are usually, but not always, shaped to achieve a kiting lifting effect. Recharging leaked lifting gas receives various solutions. W.R. Benoit U.S. Patent 4,350,897 Lighter than air wind energy conversion system by William R. Benoit, filed October 24, 1980, and issued September 21, 1982. The TWIND system is based on the use of a sail surface elevated by the climbing force of an aerostatic balloon connected to the ground by a cable, used also for energy transmission. The wind present at high altitudes creates a horizontal push on the sail which in its movement transmits this energy to the ground via the connecting cable. At the end of its movement forward, the sail surface is reduced, allowing it to move upwind with reduced energy waste. The Magen aerostat is a vertical axis wind turbine held with its axis horizontal by bridling the axis transverse to the wind so that Magnus effect lift obtains during auto-rotation. The electricity is generated with end hub generators. The LTA wind power ship uses lift from both an aerostat and wings. It operates close to neutral buoyancy and doesn't require a winch. Power is generated by turbines with the propellers on the trailing edge of the wings. The system is designed to be able to take off and land unattended. Airborne proposes to lift wind turbines into the air by use of aerostats. The electricity would return to ground loads by way of conductive tether. Airship power turbine by William J. Mouton, Jr. and David F. Thompson. The HAWP system is developed from Tiago Pardal's idea. This system consists of a pumping cycle similar to that of kite systems. In the generation phase, the pulling force increases 5 to 10 times due to the Magnus effect of a spinning cylinder. Like a kite, the pulling force produced by the aerial platform will unwind the cable and generate electricity on the ground. In the recovery phase, it rewinds the cable with no Magnus effect in the aerial platform. Non-airborne HAWP. Conceptually, two adjacent mountains or artificial buildings or towers could have a wind turbine suspended between them by use of cables. When HAWP is cabled between two mountain tops across a valley, the HAWP device is not airborne, but borne up by the cable system. No such systems are known to be in use, though patents teach these methods. When non-cabled bridges are the foundation for holding wind turbines high above the ground, then these are grouped with conventional towered turbines and are outside the intent of HAWP, where the tethering and airborne system is foundational. HAWP safety, lightning, aircraft traffic, emergency procedures, system inspections, visibility marking of system parts and its tethers, electrical safety, runaway wing procedures, overpowering controls, appropriate mooring, and more form the safety environment for HAWP systems. Challenges of HAWP as an emerging industry. There have been several periods of high interest in HAWP before the contemporary activity. The first period had a high focus on pulling carriages over the lands and capturing atmospheric electricity and lightning for human use. The second period was in the 1970s and 1980s, when research and investment flourished. A drop in oil price resulted in no significant installations of HAWP. Return on investment has been the key parameter that remains in focus in the current development activity, while in the background is the renewable and sustainable energy movement supporting wind power of any kind, but HAWP must compete on par with conventional towered solutions.